Solid is overrated.
Overrated.
Coming from a science and engineering background where numbers and statistics really show that one thing is better than the other, well, solid doesn't really do that. The terms in solid that make up the acronym are based in subjectivity as opposed to objectivity. Well, maybe except the L, which is based around objectivity, but we can get into that later. I admit, I do like the principles behind solid. It's a good goal to strive for. It makes the code more readable and maintainable. But it is just my opinion as to how readable and maintainable my solid code is. There's no metric to say that this is a solid score of 9.3 on a scale of 0 to 10. Likewise, there's no way to look at someone else's code and say this is more solid than another piece of code. I'm of the opinion that the code written by me is flawless. Everybody else's code is crap. But that's the naive approach of looking at this. People are going to look at my code, my flawless code, and think, yeah, this code is pretty crap too, and probably doesn't follow solid at all. For this video, I'm going to cover the article, The Solid Principles of Object-Oriented Programming Explained in Plain English. Now I want to note that I don't have any issues with the author of this article or of the organization Free Code Camp. I think they should continue writing great articles and helping my developer community. I did pick this article because it was the first result in a Google search for the solid principles. It was actually the second result. I skipped the Wikipedia article as number one. It just is indicative of the issues I see in solid that I want to change for future viewers of this video. I also want to note that the way the article presents solid is the way I followed solid for many years in my professional career. Lastly, this is a contrived example. The journey of how to apply the solid principles was already known before the article was written. Unfortunately, day-to-day software development doesn't work this way. You don't know the journey you're going to take and the goal you're going to meet before you start writing your code for the day. This example illustrates a journey that's already been taken for a goal that's already been met to show the solid principles. The simplicity of how to apply these solid principles is the actual issue that I think arises for how people apply these within their actual code base. Let's start with the S, the single responsibility principle. Off the bat, I just want to say that this is probably the most quoted, used, and abused principle in solid. I don't think there's ever been a time where someone has approached me and said, I'm doing this design decision because of the single responsibility principle. I'd give someone a cookie if they said, I'm going to do this because this will violate the Liskov substitution principle. By the way, the Liskov substitution principle is the L in solid. The example the article uses is a store that sells books, and when a book is sold, it generates an invoice. And in that invoice class, it has the book, the quantity of the book sold, the discount rate, and the tax rate. Now it uses these to calculate the total in the calculate total method in the invoice class. It also has the ability to print the invoice in the print invoice method, and it also has the ability to persist the invoice in the save to file method. The article argues that this violates the single responsibility principle. So for instance, if I needed to change the calculation logic, I would only have to go into the calculate total method for updates. If I needed to update the printing of the invoice logic, I would only have to go into the print invoice method to change. And lastly, if I needed to update the persistence for memory for the invoice, I would only have to go to the save to file method. This has three distinct responsibilities. This
Violates the single responsibility principle.
Moving two of the three methods, print invoice and save to file, into their own classes, invoice printer and invoice persistence respectively, makes the violation resolved. Or has it? And at what cost? The article never shows the original caller of the methods in the invoice class. Doesn't that class need to change to incorporate the changes that were proposed by the article? what makes it more appropriate to actually violate the single responsibility principle in this other class as opposed to the invoice class? Or in other words, why prepare for a potential change that might violate the single responsibility principle by actually violating the single responsibility principle with this change? I mean, there's nothing saying, or there's no requirement coming in from the article saying that the save to file or print invoice method will actually ever change. Following this fear of change in requirements to not violate the single responsibility in the future, what happens if in the future the customer is allowed to purchase multiple books at a given time? Right now, the invoice class only supports purchasing a single book at a given quantity for that specific publication at a time. The whole invoice class would have to change to support the ability to purchase multiple publications at a given quantity for that specific publication at a given time. The single responsibility principle is violated by not only the original example given, but the change to not violate the single responsibility principle in the article. There is another approach to meet this requirement outside of just changing the invoice class. If you wanted to keep the invoice class intact, you could potentially create a class called like invoice grouping. And in this invoice grouping class, that'll contain a bunch of invoices that make up the total order of what the customer is purchasing. Now, the issue with this is that invoice class has a tax rate on it. The problem with this is the tax rate should be universal across all the invoices. So if for some reason one of the invoice classes had a different tax rate, that would be a bug in the system. The tax rate should actually be at the invoice grouping class level as opposed to the invoice class level. So again, this would violate the single responsibility principle because you'd have to update multiple classes for this functionality to work. This is where opinion and subjectivity come into play. There is no universal idea as to what an invoice's single responsibility is. There is no objective truth that can be discovered as to what an invoice's single responsibility is that everyone agrees upon and no one can argue against. What's wrong with going that additional extra step and pulling out the calculate total method from the invoice class and putting it in an invoice calculator class? I mean, the result is an anemic domain model anti-pattern where there's no behavior with the data, but at least the single responsibility principle is still intact. There's a balance here as to putting too much into the invoice class and putting nothing into the invoice class. It's up to the developer to decide what that balance is. In the article, the author gave the suggestion and that works for him. That makes the single responsibility work for him. In my opinion, I wouldn't change anything from the original example he gave that was violating the single responsibility principle. There are no new requirements coming in to facilitate needing a change to any of the implementation that currently existed. The O in SOLID stands for the open-close principle. The open-close principle states that a class should be open for extension, but closed for modification. So in other words, adding additional functionality to your system doesn't require you to change code to an existing class. The article achieves the open-close principle through the use of explicit interfaces. At the start, there was an invoice persistence class that had two methods in it. One was save to file, which persisted an invoice to the file system. The other was save to database, which persisted the invoice to a database. We fixed this open-close principle by adding a invoice persistence interface instead that has two concrete implementations that implement that interface. One is file persistence, and the other is database persistence. I actually agree with the design here. I don't see any issues with how the article implemented a solution for following the open-close principle. What I can critique, though, is how they arrived at reaching this implementation. If there was an actual requirement that your boss did actually come about and say, we need to persist the invoice to the file system and the database, then this is good. If you're hypothesizing that your boss will come around and say they need to persist it to a file system and a database, then that is the issue. I'll reference another principle here, the KISS principle. The keep it simple, stupid principle. Keep the design of your system as simple as possible until you need the flexibility that the open-close principle grants you. There is overhead cost to implementing the open-close principle in that it takes longer to properly deliver the functionality that the business requires, and you also need to maintain the invoice persistence interface and the implementations of that interface, like the database persistence and the file persistence. You may not actually need one of them at all, but you have it in your code base. So, don't violate the Yagni principle either, the you ain't gonna need it principle. I also want to note that the implementation of the open-close principle has another trade-off. Just like the single responsibility principle had the benefit of not having to modify the invoiceprinter.print method or the invoicepersistence.savetofile method, it had the drawback of the caller of those methods needing to know how to actually call them, which in essence violated the single responsibility principle at a higher class level. The same thing happens here for the open-close principle. The trade-off here is that the invoice persistence interface is open for extension but closed for modification, but at the detriment to the calling class that needs to know which invoice persistence concrete class to actually utilize in its stead. That class violates the open-close principle. This is where subjectivity comes into play again. What are you, and hopefully your team, comfortable with? Remember, explicit interfaces has the benefit of injecting whatever dependency you want, but at the trade-off of understandability and readability. Now really think about it. Is there really an issue of having two methods in the invoice persistence class that persist? Do you ever expect to touch this code again? I don't know the right answers. There are no right answers. There's just the answers that the author of the article thought were best. That's what I want you to do. I want you to think about these questions and think about what your answers are when you apply principles like the open-close principle. Lastly, there is the issue of prematurely picking the wrong explicit interface to fix the open-close principle. The invoice persistence interface was supposed to do that. But what happens in the future if the save method requires an additional argument, or we need an additional method in the invoice persistence interface? Well, this would then break the open-close principle because you're now modifying the invoice persistence interface. So I'm going to reiterate again from my previous video. Time and maturity really dictate what a good abstraction is. The L in solid, the Liskov substitution principle. This is the only objectively measurable principle that you know if you are applying correctly. The Liskov substitution principle states that subclasses should be substitutable for their base class. The example of a rectangle and a square is a great example of violating the Liskov substitution principle. In the real world, a square is a subtype of a rectangle. In the object-oriented world, the representation of a square is not a subtype of the representation of a rectangle. The class square isn't an actual square. It represents what a square is. The square class describes what a square is, but isn't the actual square itself. This is at the heart of what good object-oriented programming is, and to fully understand what the Liskov substitution principle states. The thing the class is doesn't correlate exactly with what the concept it represents. The example of rectangles and squares fails the Liskov substitution principle because a rectangle has properties length and width, and those properties has the ability to get that width or length, or it has the ability to set the width or the length. A square, if it inherits from a rectangle, will inherit the ability to get and set the length and the width independently. Now the problem is a square has equal length and width, but if I ever change the width independently, that the length and the width are no longer the same, I no longer have a square. This is why this fails the Liskov substitution principle. Since the method getArea is the common shared interface method across both rectangles and squares, I should be able to get the same area value for square.getArea, but I should be able to treat a square as a rectangle, so rectangle.getArea should have the same result. The problem is I don't get the same result because length and width are also, in this example, commonly shared interface methods across both rectangle and square, which, as shown, is not the case. This clearly shows this fails the Liskov substitution principle from an objective standpoint. In this example, it has been shown that the square class is not a subtype of a rectangle class. Like I said, I have no problem with this principle. Good job, article, and good job, Liskov substitution principle. The I in Solid is the interface segregation principle. This states that many client-specific interfaces are better than a general-purpose interface. The article uses the explicit interface parking lot to show the violation of the interface segregation principle. Within the interface parking lot, you have the ability to park a car, unpark a car, get the capacity of the spots still available within the lot, and it also has the ability to calculate the cost to park in the parking lot and to process the payment when you park in that parking lot. Now the problem comes into play when we add the concept of a free parking lot. Those concepts of paying and processing the payment become obsolete for this type of functionality. So in order to fix this, we added a new interface that just deals with the payment processing and calculating the total cost to park in the parking lot, and leave the parking lot interface just to have the park, unpark, and get capacity methods. This is where I urge you to give pause and thoughtfulness. These principles, especially the interface segregation principle, are good guidelines, but I wouldn't say they should be the goal. At first glance, it looks like writing out this code this way has good benefit, but this will have long-term impact on your system. Hopefully it's good, but it could be bad. The paid parking lot explicit interface inherits from the parking lot explicit interface. Now remember, the paid parking lot interface had the ability to calculate the cost for the car to park in the parking lot, and it also had the ability to process the payment for the car to park in the parking lot. What happens though if there's a show for cars that doesn't require a parking lot? Say the ability is to drive through a light show a neighborhood is putting on during the holiday season, for example. Well, the problem is the functionality to calculate the cost of a car or to process the payment for a car is now coupled to the concept of a parking lot. And in this scenario, there is no parking lot that they are going towards. This is a show. So these two interfaces should not inherit from each other. They should be independent from one another. This concept is known as a role interface. So instead of having the paid parking lot concrete class inherit from just the paid parking lot explicit interface, which inherits from the parking lot explicit interface, the paid parking lot concrete class will now inherit from something like a car paid activity role interface and the parking lot explicit interface. With this change, I can use the car paid activity role explicit interface independently, as opposed to relying on the tightly coupled paid parking lot explicit interface, which has the ability to park. So this will allow me to have such concrete class types as holiday event show and car safari. I am not saying the end result of what the article came up with to apply the interface segregation principle is incorrect. The requirements for this fictitious system in the article may be exactly what is needed for this system to function properly. But the reader lacks context as to what those requirements are. The simplistic nature of how we arrived at this solution is the problem I'm pointing out. I'm going to sound like a broken record again and again, but I think it's very important to understand that time and maturity make good abstractions and explicit interfaces, and that will help you to adhere to the interface segregation principle. Please do not create explicit interfaces when you start a new project. And please do not create more explicit interfaces off of the original explicit interfaces that you started with the new project, because those original explicit interfaces were subjectively justifiable and probably incorrect. Taking it to the extreme, what's the issue with taking all 5 functions within the explicit interface parking lot and moving them into their own explicit interface for each function that exists? So for example, the park car function can be moved into its own explicit interface, car park. The unpark car method can be moved into its own explicit interface, car unpark. You could do this for the get capacity, the calculate payment, and the process payment methods as well. This does follow the interface segregation principle, but does that really help your solution in any way? Moving away from the extreme example where every explicit interface just has one method defined in it, let's take a look at the article again and look at the free parking lot explicit interface. Well, this free parking lot explicit interface doesn't have a function within it at all. It's entirely empty. What good does this explicit interface have? Why can't it just be a concrete class? Well, I have an answer to that and I'll address it in another video. Spoiler alert, this should not exist. We have now reached the end of Solid, the D, the Dependency Inversion principle. This states that high-level modules shouldn't depend on low-level modules. They should both depend on abstractions. I pretty much covered this in my inversion of control video here from before. In there I pointed out issues that I saw with dependency injection and the dependency inversion principle in general. Also, previously in this video, the open-close principle was fixed or not violated by following the dependency inversion principle, and I pointed out kind of issues that come about when following this principle. To summarize, what I think is best to get the most out of the dependency inversion principle is to not have everything in your system be an abstraction or explicit interface. Only create an abstraction or an explicit interface if there is need for that flexibility in your code for that functionality. And please don't create these explicit interfaces or abstractions on the idea that the system may change and may require it. Only do it when you get the requirement for the system to change. Good developers write good code, and bad developers write bad code. It may be that most good developers will follow their own flavor of what they think Solid is and produce amazing code. But the same is true for bad developers. Bad developers will follow their own flavor of what they think Solid is and produce, well, bad code. The Solid principles are a good guideline to producing good explicit interfaces and abstractions. But you need the passing of time and maturity to actually utilize the Solid principles appropriately. You can't apply the Solid principles appropriately at initial development of a feature. The Solid principles are a long-term, never-reaching goal that has the idea that you will make volatile, problematic, or code that future readers will look at, understand, and navigate more easily, without the fear of potentially adding regressions to the system. But hey, again, these are just my strong opinions, weakly held of course, so please leave a comment in the section below and let's discuss.